All right, let's talk about rules of exponents. I have these 4 examples I'm going to use to build the first rules for exponents. But first I want to review what an exponent is. I'm sure we all know, but this is important to review when we go to kind of apply rules that will make sense if we understand exponents. So if I have something like 5 to the 3rd power, what that means is 5 times 5 times 5. This exponent just means repeated multiplication. Now, we don't just have numbers, we could have things, and this is going to be important for this conversation over here. If I had something like x squared to the 3rd power, now I can apply either one of these exponents, but if I apply this exponent on the outside, what it means is multiply anything I have on the inside by itself 3 times in a row. So this, if I expand this exponent right here, I would get x squared times x squared times x squared. Okay, remember that throughout these examples. It's this idea that exponents are repeated multiplication. Whatever's inside the exponent gets repeated. When we're being asked to simplify exponential expressions like this, what we're trying to do is combine the information we have into as simplest form as possible. Sometimes that will give us one factor, but sometimes that will be multiple factors simplified as much as possible. But let's develop some rules for making this nice. To develop these rules, I'm going to expand each of these as much as possible. You shouldn't have to do that in the long run, but I want to show where these rules come from. First, right over here, we have x squared times x to the 3rd. What I'm going to do is expand the x squared and the x to the 3rd, and then look to put this together into one simple expression. X squared times x to the 3rd would be x times x, and then so that's x squared, times x times x times x. So all I've done is rewritten that expression without the exponents, but now the thought is, can I combine that in any way? And I can. Because the operation connecting these two expressions is multiplication, all I have now are 5 different x's being multiplied straight together. I can simplify that expression into x to the 5th. So to develop a rule for this, what do we get? When we multiply 2 expressions that have the same bases, if we're multiplying them together, we actually can add their exponents because we can add the number of multiplications that we have right there. So first rule we have for the rules of exponents is if we have 2 things with the same base being multiplied together, we can simplify them by adding their exponents. And that's the justification right there. In this next expression, we'll expand this in the same way. So what we're doing is we have 6y's on top, or y times y times y times y times y times y, all divided by y times y. And then now what we're going to do is apply the fundamental principle of fractions that says we can cancel 1-for-1 common factors in the numerator and the denominator. Here's what that would look like. I can cancel this y with this y, and this y can cancel with this y. Important to note that when we cancel, we don't just get 0, we actually would get factors of 1. Those won't come into play too much, at least in the numerator in this case, but you'll see the reaction in the denominator, and it will be important in the future. So what do we have on top now? Well, we've canceled 2 y's in the numerator and the denominator. We have 4 y's up here. Let's put this back into an exponential expression, which would now be y to the 4th. And then we're being divided by, and this is kind of part of the important part right here, y to the 1 power. But anything over 1 is just that expression by itself, and so we'll rewrite that as just y to the 4th. So what happened? Well, we canceled 2 of the y's in the numerator with the y's in the denominator, and we got y to the 4th. In fact, this is a bit the opposite of the last expression we just dealt with. If we're going to divide exponential expressions like this, we actually are going to subtract their exponents from each other, and that's our second important rule. If we take y to the n over y to the m, we would subtract those to get y to the n minus m, or in this case, y to the 6th divided by y squared is y to the 4th. Notice the strange things going on here. When we multiply exponential expressions, we add their exponents. When we divide exponential expressions, we subtract their exponents. We don't actually divide the exponents. We divide the expressions, but the actual reaction is dividing their exponents. All right, moving on. Number 3 is the precursor I set up earlier. We have x squared to the third power. I'm going to write this as x squared times x squared times x squared. So expanding the outer exponent here. Now what I can do is actually apply rule number 1 that says if I'm multiplying exponential expressions, I add their exponents. And so I can do that all together here. That would be 2 plus 2 plus 2, which is 6. So I'm applying rule number 1 right here, and I get x to the 6th. The question is, what is actually happening when I'm doing that? What's a quicker way for getting from here to here? Well, when I expand the x to the 3 on the outside, the exponent of 3, I get 3 copies of x squared, and then I'm going to add those together. So repeated addition is actually multiplication. The quick way to have gone from this expression to this expression would have been simply to multiply this exponent by that exponent. And so that gives us our third rule of exponents, which is if we have an expression, an exponential expression with an exponent on the outside, we can simply multiply those exponents together. What I'm going to do with this expression is exactly the same thing I did with number 3. I'm going to expand this expression on the inside 3 multiples. I'm multiplying these together. The important thing to remember is that between these, the x squared and the y cubed is also multiplication. Now I can employ the concept of the associative and commutative properties of multiplication. I can rearrange these in any way that I want. I will do it in a specific way to make the point that I'm trying to make right now. I'm going to put all the x squareds together and then the y cubes together. And what I want to show you now is then I can actually use, do the opposite of what I did number 3 and go from this kind of expression to this kind of expression. I want to show you what the result is. What I get is here I have x squared to the third power. So I have an x squared to the third power and a y cubed to the third power. I actually could then apply rule number 3 to these and make this an x to the 6th and a y to the 9th. But the one thing I wanted to highlight was what actually happens here is the exponent on the outside here, I'm going to use the word distribute, but it's not actually distribution, but it makes sense in the way that thinking of this 3 gets applied to each of these factors or distributed of sorts to each of these factors to be this right here. So the rule that we have from this is that this exponent applies to both of the things on the inside. It distributes of sorts to both of those factors. And I won't show an example of it, but this actually works for division or fractional expressions also. We call those rational expressions. If I had x over y to the nth power, that n applies to both the numerator and the denominator. In real life examples, we're going to be using multiple of these at a time, and there'll be many more examples of that, but these are the 5 base properties of exponents.